Okay, guys, chapter 21, part 2, last part of respiratory system. Let's jump right on in here. Okay, we talked about some of these volumes. There's a new one on this one. This is one of the booths that you find in a pulmonologist office when they're trying to do the spirometry, the measurement of the airflow. So we talked about the expiratory reserve volume, total lung capacity, residual. We talked about the functional residual capacity. We talked about the slow lung capacity. Now, this is one that we didn't talk about that's used considerably. Forced expiratory volume. They actually do this FEV with a little 1 to indicate the amount of air that can be forcibly expired or exhaled in a 1 second period of time. Usually it's about 80% of the total expiratory volume. This is something they use in order to diagnose COPD, um, chronic obstructive pulmonary disease. It's an inability to move things out, forced vital capacity, the volume air that is exhaled after maximum inhalation. Okay, as far as arterial blood gases, we do use these sometimes in the hospital. They're very painful because we have to take the blood from the arteries. We can't take it from the veins because that would not give us the same oxygen and CO2 concentrations. Sometimes it's necessary, but it's rather painful and difficult to do, but sometimes we have to get those. Okay, respiratory rate, control of ventilation. Respiratory rate is simply, and this is usually abbreviated RR on our charts, is simply the number of breaths taken per minute. Normal is anywhere between 12 to 20. Most folks, when I check the charts and I know my nurse has been lazy, almost all of her patients have a respiratory rate of 20. That's not very likely. But in any case, we take these. Now, the way we do this, your patient knows that you are actually counting the respirations, their conscious mind will override and it will change it. So what we usually do is we continue to make out like we're taking the pulse and at the same time very unobtrusively glance to watch the rise and the fall of the chest and get our respiratory rate. Okay, as far as the control, we have the medulla and the pons. In the medulla, we've got the DRG and the VRG. The DRG is right here, and there's the VRG. As far as this is the DRG is going to give us our constant rhythm. It's going to be the one to send the signal to the intercostals and to the diaphragm, signaling for them to contract in sequence according to the rhythm. So you might say this is the guy that's going to be in control of quiet breathing. Now the VRG, on the other hand, is for forced breathing, when we have to go above and beyond our quiet breathing, our tidal volume, and bring in much more and expel much more. These guys are going to stimulate those accessory muscles of respiration. Which we'll get to here in a minute. As far as the pontine respiratory group, we've got the apneustic center, which is going to determine the depth of our inspiration, how deep of a breath. And then we have the pneumotaxic center. And this is going to be the one that's going to actually inhibit the DRG so that the rate can be controlled at a much faster pace. or slower pace for that matter, but mostly faster. Okay, guys, let's see. I think we got some more over here. What are the things that affect our respiration? There are certain conditions, stimuli, that when these guys increase, it's going to cause us to increase the rate that we breathe in and the depth to bring in more oxygen. In other words, we have chemoreceptors that watch increasing carbon dioxide levels and hydrogen ion levels, which is the same as pH. Now, as the hydrogen ions go up and the pH goes down, then this will be a stimulus for us to take deeper breaths. We're going to talk about a lot of other things involved in it in just a few slides down the show, but and really increasing CO2 and increasing hydrogen ion levels, those are kind of the same thing. We'll talk about those in the appropriate place. So we have chemoreceptors in the brain and the brainstem, which are going to be our central receptors. In the medulla, we're going to have these. We're going to have them in the brain itself. And what these guys are actually looking for is these hydrogen ions, because if the CO2 goes up, the hydrogen ions will go up as well. And I'll explain why that's so a little bit further down. Those are peripheral chemoreceptors in the carotid artery and the arch of the aorta. If you remember, we also have baroreceptors there for pressure. We have these guys as well. There are some receptors in the muscles and joints. We also have, and that's of course our respiratory centers, we got stretch receptors in the lungs. This goes in to allow the medulla respiratory centers to have an idea of where we are in the respiratory cycle, whether the lungs are inflated or deflated. We also have irritant receptors, and this is going to be for our cough reflex. If we get any kind of irritation in the trachea or the bronchi, then we initiate a cough reflex. We violently expel air and attempt to loosen the irritant and push it out. We also have an increase in this from the hypothalamus and the limbic system. Remember, the emotional system is tied into the hypothalamus, which is tied into the autonomic nervous system. So pain, strong emotions, or temperature increase, all of these things will cause us to breathe fast as well. Hyperventilate. Okay, gas exchange, gas laws. Now, we talked about Boyle's law in the first part. Now we're going to talk about Dalton's law. Do you need to know that? Well, I just circled it so you figure it out. So we said on the first that the pressure of the atmosphere at sea level was 760 millimeters of mercury. Now, we didn't talk about the individual gases that make up our atmosphere. So most of the atmosphere is nitrogen, and let's see, I believe that's like, 22%, 21% oxygen, and somewhere around 78% nitrogen, with less than 1% being all the other gases, hydrogen, helium, krypton, neon, blah blah blah. But what we're saying is that that pressure, and they're just showing the pressure of the oxygen and the nitrogen together. If we add all the other trace gases, it adds up to 760. So we're saying that atmospheric pressure is made up of these components. The pressure of oxygen within the atmosphere is 159. The pressure of nitrogen is 593. So what we're saying is partial pressures. This is Dalton's law. Each gas that's in a mixture, such as our atmosphere, has its own pressure. When you total all the partial pressures, then you get the total pressure. Okay, so that's all partial pressure is the part of a total pressure that is exerted by a single gas. We already know gas moves from high to low pressures, and this kind of makes sense. The steeper the gradient, the faster they move. So if I had a hill like this or a hill like this, and you were to let go of a ball, which one do you think would go faster? Well, the steeper the gradient. That's exactly right. So the more difference, or the greater the difference is in a gradient, then the faster it's going to move. And this is not just academic, guys. This is actually needed for our understanding of how we're going to do our respiration. Gas exchange, alveolar ventilation. This is where the air that comes in through the conducting system, the bronchi and the bronchioles, is actually swapped out. So this is what we know. The amount of carbon dioxide in the alveola is way higher than the amount that's coming in the air that you breathe. So we would expect carbon dioxide to move down its diffusion gradient in this direction. On the other hand, the amount of oxygen in the alveoli is considerably less than the amount that's coming into the incoming air, and so we would expect oxygen to move in like this. So there's just an example of our gradient. Now here we're going to be talking about the solubility of gases. So Henry's law, another law, the concentration, the amount of gas in a liquid depends on how soluble it is, can it dissolve in a liquid, and on the partial pressure. So why do we say that? Because we remember we talked about that the turbinates in the nose actually help to warm and humidify, add water vapor to the air, because in here we've got water, a little bit, the film that's being kept apart by the surfactant, but it's solute. This stuff is kind of solid, dissolved in the water vapor. The air in the alveoli has much more water vapor and more carbon dioxide, but less oxygen. We've already talked about that. Now this is, when I say more and less, I'm actually talking about the partial pressure. We said, let's go back one, the partial pressure of oxygen in the incoming air is about 159. Let's just round that to 160. That's 160 for the O2 there. The O2 in the alveoli runs around 105. So this is a pretty good gradient. There's considerably more oxygen here. So the oxygen is going to come into the alveoli, and it's going to, oxygen does not dissolve well in liquids, but the partial pressures are such that it's going to move in there. Okay. So, and obviously the partial pressure, I'm trying to remember, guys. I think it's around 40. Don't quote me on that. And the partial pressure of carbon dioxide in the incoming air has got to be very low, but it's going to definitely move up down that route. Okay. Continuing onward. gas exchange, ventilation, and perfusion. Ventilation is the movement of air into the alveoli and the movement of waste gases like CO2 out. Perfusion is the amount of blood that's coming by there. So this is the thing. We need to have a match between the amount of oxygen coming in and the amount of blood vessels. If we have more oxygen than we have blood flow, then that oxygen is wasted and it's not going to be taken in. If we have more blood vessels and have less oxygen, then we're wasting the blood flow through that area. So we want to have this matched. So there's our ventilation and perfusion. We want to balance it. Matched is a better word. If it's unmatched, if it's not optimally, so in this illustration, we're showing that we've got less oxygen coming in. So as a result of that, those arterioles are going to constrict. Remember those? And we're going to shunt that blood around and away from it, because if there's not a lot of oxygen there, there's no point in sending a lot of blood flow there. On the other hand, if the oxygen levels are higher than the blood, then we need to open those muscles and let the blood flow in there. In general, it's not going to be totally balanced. There is more oxygen at the top of the lung and there are more blood vessels at the bottom. So there's going to be a mismatch there. And of course, right in the middle is where we're going to get our best match. It's not that if these guys aren't matched up, they can't work. It's not that. It's just that to get the best, the optimal performance, that's what we need. Okay, we're not going to talk about this right here. We're going to talk about this in a little bit, all of this going on. Okay, so we talked about alveolar perfusion. Now we're going to talk about external respiration. What is external respiration? That's where the oxygen in here leaves, goes into the blood, and eventually makes its way into the red cells. The CO2 that is in the blood is going to cross this respiratory membrane and come into the alveolus. Okay guys, so what we're doing here is moving the gas out from the alveoli into the blood. The reason we can do that is, again, the partial pressure of gas, of oxygen specifically, is about 105 there. Here, it's about 40. There's a big, huge difference. This difference is going to cause the oxygen to move very rapidly, which is what we need, because it's not like the blood cells can stop, pick them up, and then go. They're saying about 64, whatever, somewhere around there. The partial pressure of carbon dioxide is going to be higher out here. I think it's about 40 here. Must be lower there in order for it to move. Now, CO2 gradient is not as steep, but CO2 is more soluble. It dissolves easier in water. So that's what helps it to move fast because of its solubility. The oxygen is less soluble, but we have a steeper gradient, and that's going to move it very quickly. That's external respiration, the movement of gases from the alveoli into the blood and vice versa. Why was I saying external respiration? Because then we've got one we call internal respiration. Internal respiration, we're doing the same thing, only we're moving the different gases. Oxygen is leaving the blood vessels and moving into the tissues. CO2 is leaving the tissues and moving into the blood. Now, the CO2 is going to be higher in the tissues because they're undergoing the cellular respiration, the breaking down of glucose. they're using oxygen up, so that's keeping the levels low, and they're producing CO2 as a byproduct, which is keeping their levels high. So we're still using the partial pressure gradients, only the partial pressure of, of this, and here the partial pressure, we didn't show it there on the external, but we said it was 40 and 105 the alveoli, 40 in the blood. Oxygen moves and actually raises this to about 100. And then the partial pressure of oxygen here is about 40. So again, we have that steep gradient, and even though oxygen isn't very dissolvable in water, it's going to move fast. Here we're going to have the same thing. We're going to have a lower CO2 level in the blood, and we're going to have the CO2 move. Again, it is going to be more soluble. Okay, guys, I think that's everything I wanted to say on that. Gas exchange hyperbaric. You may have heard about this. There are places where we put people in specially constructed chambers, and then we increase the pressure way up above atmospheric. Remember, atmospheric was 760. You might even be able to go to 2 atmospheres, which will be somewhere around 1600, 1500. I'm not going to do the exact math. It doesn't matter. But we're going to go higher. Now, if the pressure of oxygen is higher in the atmosphere, that means more oxygen is going into the alveoli because the alveoli are still going to stay down. The more oxygen goes into the alveoli, the higher the alveolar pressure, which is going to move it that much faster into the blood, and it's going to reach a higher level of partial pressure, and when it gets to the tissues, it's going to move large amounts of oxygen fast. We use this for wound and graft healing, especially on anaerobic bacterial infections. We flood the body with oxygen in doing this, and the anaerobic bacteria, they don't have the ability to live in an oxygen atmosphere, and it kills them. Or if a person has carbon monoxide poisoning, carbon monoxide, just CO, binds to the hemoglobin very, very tightly, more tightly than oxygen does. That's why people die from carbon monoxide poisoning. It actually winds up tying up all your hemoglobin, and you have no way to carry oxygen to your body. But by having this increased partial pressure, trying to push the carbon monoxide off and get oxygen back on there. Okay, guys, a little bit more detail now. We've already said that oxygen isn't very soluble. Of all the oxygen we take in, maybe 1 to 2% is going to be dissolved in the plasma. The rest of it is going to be bound to the heme groups in the middle of the hemoglobins. So we have 4 heme groups, so we can get 4 molecules of oxygen in there. They're going to bind to that at the very center of the heme group is an iron with a +2. So we're going to be able to bind the oxygen pretty well there. This is how most of it is going to be transported in the blood from the lungs to the body. A little bit of terminology, you know they test this. Oxyhemoglobin, that's what you call the hemoglobin when the oxygen is bound to it. Now this is something, so I've got 4 spots. This is something that's kind of interesting. The first oxygen, well, heme doesn't have that great of an affinity for the first one. But if once one is bound, the second one goes on easier. Once the second is bound, the third goes on easier. And finally, the fourth is the easiest of all. Binding the first oxygen is the tough part, but the rest of them heme becomes more attracted to the oxygen. Saturation. Now, with my 4 spaces on the heme group, it's kind of obvious, I think, that if I've got 1 bound there, then that's 25% saturated. 2 is 50, 3 is 75%, and of course 4 will be 100%. But when they're talking about saturation, they're not talking about individual heme molecules. They're talking about all of the hemoglobin. On average, if you're in really good shape, over 98% of your heme will be fully bound with oxygen after it passes through the lungs. That's what we actually measure with the pulse oximeter, the pulse ox, that little device they stick on your index finger. Okay, guys, let's not panic every time we see a graph. This is actually pretty easy. So there's the oxygen saturation. Now here I am going to talk about just a single heme molecule to give it an illustration. So there's the partial pressure. Remember we said it was around 105? So at the lungs, the partial pressure is going to be 100%, and we're going to be 100% saturated. In other words, at the lungs, when the partial pressure is 100, then all 4 heme sites on a hemoglobin molecule are fully bound. Now, this is from the lungs. As we go to the tissues, I said that it drops down to 40. Now, at 40 millimeters, then we're going to drop off. We're going to drop down to 75% saturation. In other words, we're going to actually release 1 oxygen molecule to go to the tissues, and then the rest of the hemoglobin is going to keep the 3. And in many cases, that's what happens, is that with a normal partial pressure of oxygen of 40 in the tissues, then the heme is only going to, it's going to lose its affinity for one of its oxygens. In other words, it's going to drop it off. Now that's fine, and then this guy goes back around. He goes, let me go and draw this. He goes back to the lungs, picks up another one, and continues on and on and on. Now what would happen if the pressure was 30 in the let me draw that one again, guys. That looks kind of pitiful. This is about 30. Somewhere around 50%. That would probably be more like it. But about 50%. So if the partial pressure in the tissues drop from 40 to 30, then I'm going to be dropping off an extra oxygen. And instead of having 3 to go back to the lungs, I'm going back with 2. When would the partial pressure of oxygen drop from 40 to 30 in the tissues? When they're working hard and they're using it up. Think about skeletal muscle during maybe exercise or running. You're burning, you're using a lot of oxygen to make a lot of ATP to keep the muscles moving. So we're going to use it up, and the partial pressure of oxygen in the tissues is going to drop. What would happen if my partial pressure went from 30 to 20? We're going to be right around 25% saturation. What does that mean? It means I'm going to drop off 3 of my hemoglobins, and then I'm going back to the lungs to pick up 3 more. So this is called an oxygen hemoglobin dissociation curve. That's a mouthful, but all we're really saying is this shows us how we drop, how and how many oxygens we drop off. It really depends on the partial pressure in the tissues, right? Now up here, this thing is more vertically, this guy's almost horizontal. What if the pressure in the lungs dropped from 100 to 80? Well, look at there. I would probably drop from 100 to maybe 95%. No, it looks more like 98. See, it's not going to have as much of an effect. So even if the partial pressure in the lungs drops, it's not going to have a lot of effect on how much oxygen is loaded onto hemoglobin. What's going to determine how much oxygen is released from hemoglobin is how bad the situation is in the tissues. How low are they on oxygen? It makes kind of sense, guys. If you had a, it's kind of hard for you guys to to think back because you never had milkmen, but if you had a guy delivering and milk, for example, and you put out 3 glass bottles, then he would put 3 bottles of milk there to replace them. If you had 2, then he would put 2. That's the way they do when they stock in like stores. A lot of these guys, milk companies, drink companies, they'll come in, see how much has been sold, and they'll replace what's been sold. So the lower the oxygen goes in the tissue, the more hemoglobin we drop off. That's all this is saying. Now, that's the normal curve. It actually can get a little bit abnormal. Let me back off some of my drawings because I want to draw you some more curves. Well, that's as far as it'll let me back it off. That's okay. Now, let's make sure we get finished with all this. I think I've told you everything here. More about, we already talked about that, and we talked about that. Temperature and the pH will also affect the oxygen hemoglobin curve. This is what happens, guys. If the pH goes up, then this whole curve shifts over to the right. What does that mean? Do you remember where I would have to have a 40 to drop off 1? Now to drop off 1, I can drop it off at a 60 and everything shifts over. So what's going to cause this shift to the right? Well, higher temperatures, higher pH. Well, higher temperatures means the tissues are working hard, generating heat, so they need more oxygen. pH means that we're building up not only CO2, but you guys remember lactate? When we don't have enough oxygen to do aerobic respiration, we switch to glycolysis. We take that pyruvate and turn it into lactate, and lactate is also known as lactic acid. So that's going to shift the curve to the right, and by doing that, it's going to make it easier for us to drop off oxygen, because if we've got high temperatures, high pH, then without a doubt, or high CO2 as well, which is almost the same as a pH, then that makes sense, guys, that we're going to be more willing to drop off more oxygen at less of a partial pressure difference. We can also have the curve shifted to the left over here, which is going to mean that I'm going to retain my oxygen longer, and it's going to take more to get me to drop it off. Well, what's going to shift the curve to the left? Just the opposite. The pH goes way high, which means I'm alkalotic, or the temperature is low, CO2 is low, then I'm not going to tend to be dropping off as much oxygen. That's what all these curves mean. I know curves, math scares everybody, but really, guys, this couldn't be simpler. It's super simple. We're only saying that we're going to follow the partial pressure gradient if everything is normal. But if the pH is low, if we're very acidic, or we have a lot of CO2, or the temperature is rising, then we're going to shift the curve to the right and make it easier. Oh, I didn't have to do that. They had it all over here. I knew that. I forgot. Anyway, those are different curves. I'm not sure what their 10FC is, unless that's temperature. Yeah, that's what it is. So 38, which is about normal body temperature. And if your body temperature goes higher, then the curve shifts to the right. And again, there's a 50% mark. We're shifting everything over 75, I'm guessing about right there. So I'm willing to drop off oxygen somewhere around 60. And the same thing for the leftward shifts. 20 degrees, I'm a little bit cooler, and you notice that this thing goes further to the left. Some oxygen remains bound to venous blood. We already said that. That depending, we can drop off, we could drop off all four, but to be 100%, but the partial pressure would have to be close to 0 to do that. So now I was talking about a single hemoglobin molecule. This same thing applies as to the saturation of all the hemoglobin. It's just a matter of scale, but the principle is the same, guys. Now I really do want you guys to spend a little bit of time on this curve to understand it. That's the exact same thing as we saw in the other one. Effects of pH, we already talked about it. Lactic, carbonic acid, carbon dioxide. Relationship between metabolism, temperature, and pH. Well, obviously, the faster and the more biochemistry you're doing, the higher the temperature and the more oxygen you're using, you are going to eventually get to a point where you have to switch to glycolysis, and that's going to drop the pH. Okay, hemoglobin of the fetus. This is kind of interesting. Now, this is the adult hemoglobin, but we've also got a fetal hemoglobin, and it's different than the adult. And this is, we make this while we're in utero and sometime afterward. And if you look there at the blue curve, that's the dissociation curve for fetal hemoglobin. This guy is more attracted to oxygen than the adult hemoglobin. So this is a uterine artery. This is mom's artery. There's red cells with oxygen. Now, just like in the tissues, this is inside the chorionic villi. This is the baby's blood system. There's going to be a difference in pressure between the oxygen here and in there, which is going to cause a net flow of oxygen. And the fact that this hemoglobin is so much more, has such a greater affinity, is going to assist with that. And again, the CO2 levels here are going to be higher, and that's going to cause the CO2 to go back into mom's circulation. That's how the baby breathes during gestation. Chorion, that's where the mom, we talked about that. Very important, fetal and maternal blood do not mix except at delivery, and that's, of course, a traumatic thing with all kinds of bleeding and stuff going on. The higher affinity, the partial pressure difference is not as dramatic as it is in other places, so that higher affinity helps to even things out. Okay, guys, we're going to talk about some of that stuff that I showed you earlier. CO2 transport. Some CO2 dissolves into the blood directly. It's more soluble than oxygen. Some CO2 binds to hemoglobin. It does not bind to the heme group like oxygen does. It actually binds to another part of that protein chain, but it binds. And when that happens, it's called carboxyhemoglobin. Another terminology question. But a lot of hemoglobin, the majority of it, is going to be converted. And I'll show you this coming up. Say 70%. I've seen higher figures. 20% is about right. Dissolved, around 10. That's good. I'm not too particularly concerned with exact numbers, just proportions. Okay, this is where it's happening. Excuse me, carbon dioxide and water. And then there's an enzyme that they're not showing you here, but they're writing it here. Carbonic anhydrase is going to take these guys, rearrange them, and turn it into carbonic acid, H2O, CO2. So I've got 2 H's, 1 C, and 3 oxygens. There it is. Now, like this is an acid, and we know acids tend to spontaneously drop off hydrogen ions, and this is what happens. The carbonic acid is going to dissociate. It's going to break down. One of the hydrogens is going to go free as a hydrogen ion. The remainder of that is going to be a base called bicarbonate. It can go even further, but I'm not really concerned about this right now. We really can do fine with just this. Now, this reaction can go either way. It depends on how much of each you have. So there's the carbon dioxide coming from the tissues. This carbon dioxide with the water and with the without the carbonic anhydrase, this is why they got it marked as slow. We'll eventually kind of make this and go ahead and break down into bicarb, and then that hydrogen ion is going to bind itself to some plasma proteins. This is the majority is going to use that enzyme breakdown, and then basically the same thing. Now, when the bicarb, this is the inside of the red cell. When the bicarb goes out, it's a negative, it's an anion. Then the chloride has to go in to balance it, because if I push a negative charge out, I need to bring one in. That's called the chloride shift. So this is all at the tissues. We're picking up CO2 from the tissues. Carbaminohemoglobin, there's our CO2 directly bound to the hemoglobin. And then there's the oxyhemoglobin breaking the oxygen off, going into the tissues, and then whatever small amounts dissolve. And then that hemoglobin is going to bound itself with that hydrogen. So that's the way that we transport most of our CO2. We turn it into carbon dioxide and water into carbonic acid, which dissociates into hydrogen ions and bicarb. Now, at the lungs, we do the exact opposite. We take carbonic anhydrase, so it's also going to catalyze this reaction. We're going to move it the other way. We're going to take that hydrogen ion, the bicarb, turn it back into carbonic acid, and then we're going to break it apart into CO2 and water. The CO2 is going to diffuse into the lungs and then get breathed out. So that's how most of this is going to be transported as bicarb. Talked about that. Bicarb moving out and chlorine going in. And then we've already said the reaction, that's what the RXN means, is reversed at the pulmonary capillaries in the lungs. Okay, more. 20%, we've talked about that. The pressure, the partial pressures are going to be what's going to cause this dissociation and the binding. Oxygen saturation is also going to affect the CO2 binding. And here's another little tidbit for you guys. Actually, I got two. The Haldane effect. Hemoglobin that is fully saturated with oxygen isn't going to want to let the CO2 bind, even though it's not binding in the same place. It's going to have a lower affinity. It's not going to bind as much CO2. That's the Haldane effect. That's going to be something you're going to need to know, guys. The Bohr effect, another one. If you increase the carbon dioxide, and that's going to decrease the pH because we're going to be making hydrogen ions, this is going to lower the hemoglobin's affinity for oxygen, causing its release. We actually did that when we talked about our right shift. The pH goes down, then that's going to move things. So there's our 75% point right there at about 50. And here's our 50 or 75% point at 60. So by having that Bohr effect, increased CO2, which is also going to be the same as decreased pH, then we're going to actually shift the curve over, and we're going to make it easier for oxygen to drop off from the hemoglobin. Okay, respiratory functions. Hyperpnea is rapid breathing. So we breathe deeper and faster when we have more need of oxygen. We don't really alter the levels of gas in our blood because we're dropping off the extra that we're taking in. Hyperventilation. Now, hyperventilation can actually, you're breathing deeper, you're breathing faster, but you don't need to. There is no reason for it. It's not an increase in oxygen need that has led to this. This is totally different. This is actually going to be detrimental because it's going to actually, you're going to lose more of your carbon dioxide. Your carbon dioxide levels will go down. And this is not really a good thing. We'll talk about that when we get to the acid-base chapter. But there's a big tie-in between the respiratory and acid-base. But I won't talk about that at the appropriate place and not right now, guys. But anyway, that's the difference between hyperventilation and hyperpnea. Hyperpnea, I'm breathing faster, but that's because I need more oxygen. Yeah, hyperventilation, I'm breathing faster, and it has nothing to do with the oxygen needs of the body. This is the kind of thing that the limbic system gets involved. Exercise does not cause hyperpnea. Ventilation is increased before the oxygen levels actually start to drop, and they do have a rather complex system for regulating that. Okay, here's something. We're probably about right here in Cobb, Bartow. We're at about 1,000 feet elevation, and there's, of course, is the sea level. Now, if you've ever been out west, that's about, excuse me, try that again. This is about where the Grand Canyon and Yellowstone Park is about 8,000 feet. It's actually, you can definitely get mountain sickness or altitude sickness. What happens is there is less oxygen there. Is the oxygen still 21%? Yes, it is, but there's less of everything. There's less total gas there, including the oxygen. Because of that decrease in the amount of oxygen, the partial pressure goes down. If the partial pressure goes down, then that means we're not going to be moving as much oxygen as rapidly because we're dependent upon that gradient, that difference concentration gradient to move it both into the alveoli and then into the blood after that. So what's going to happen then, since we're not moving as much, our hemoglobin saturation is going to drop. If you don't have enough hemoglobin, it's the same actual physical symptoms as anemia. You're going to feel tired and weak and all this stuff because you're simply not getting. Now, at sea level, hemoglobin is higher, but we're not releasing as many molecules into the tissues. We may only release 1 out of the 4. At higher altitudes, we're going to release more because we're going to be shifting that dissociation curve to the right. Now, BPG is an intermediate that is involved in glycolysis. So the more glycolysis, you produce more BPG because you're doing more glycolysis. That's also going to help push the curve to the right. Eventually, most people get a form of polycythemia, not a pathological. You're going to get more red blood cells. You're going to make more red cells so that there's more oxygen can be transported, even at the lower partial pressures. But that's why, and of course up here, which is Mount Everest, you will die very quickly there. At about 29,000 feet, you will not last long unless you've got a bottle of oxygen you're breathing from, because it's simply not enough air to sustain life. And a lot of folks have died up there proving that over and over and over. Embryonic development of the respiratory. So this broad embryonic and fetal period, basically during gestation. The first thing we're going to do is make the conducting zone, which makes sense. You're going to start at the larger and go smaller, making all the bronchioles. And then we're going to make the terminal bronchioles, the bronchi, the bronchioles. And then during this canalicular, you don't have to know any of this, guys. It's just an overview showing you how the respiratory system develops in utero. We're going to make the respiratory bronchioles and then finally the alveolar ducts. That is just all those holes, those pores in the alveoli. And finally, we're going to make the sacs. We're going to make the respiratory zone last, transitional and then respiratory. We're going from the highest level to the lowest level. Now notice that here is we start making surfactant. This is one of the problems with premature babies. They get respiratory distress syndrome. We generally try to give them a steroid before they're born because that will increase the surfactant. The problem is if those alveoli, if the water is allowed to cling together, the hydrogen bonding, the alveoli will collapse, and it will take a lot of effort, maybe too much effort, to open it up. So this is a problem for the babies. And here's some pictures of neonatal respiratory distress. This one is more severe. Guys, you see the black area right there? That's the way lungs are supposed to look. Air does not block x-rays at all. Therefore, the x-rays go straight through and hit the film and turn it black. Water is a whitish. Here you can barely see the lungs. You see specks of blacks, but it's almost washed out. Here you see some fluid there, but not quite as severe. So that's a big thing with our preemies. They're going to have poor gas exchange. Dyspnea means their breathing is going to be irregular. Low oxygen, high CO2 levels. This can cause septicemia. That fluid buildup in there can be an ideal breeding ground for bacteria. Pulmonary hemorrhage can start bleeding in the lungs. treatment, resuscitation, intubation, CPAP, pulmonary surfactant administration. We generally do as I said, the steroid injections. All right, guys, that's everything with respiratory, and it's everything for exam number 2. All right, thanks, guys.